get started forthwith. We covered gradient descent last time. We realized that when you do gradient descent, it gradually takes you to a minima. There are a couple of interesting questions that come up. First of all, why is it that you don't use, for example, just take the derivative and set it to 0 and so forth. It's not feasible from a computational perspective. So in low dimensions it's possible. When you have a huge data sets and high dimensional spaces, it's not practical. Gradient descent and the whole family of gradient descent are the practical choices. Then we will discuss today. So the topics that we'll cover today is, I'll assume that you understand gradient descent. I'll remind you what it is. We'll talk about the loss landscape. Then we'll talk about something called regularization, which is an important topic. We have covered it in the previous workshops, those of you who attended it. But nonetheless, we'll do a refresher. And for those of you who are new to this topic, it is an important topic worth paying attention to. Once we have done that, we'll focus on, we'll see how the loss surface responds to these things, to regularizations, various techniques of regularization, how it responds to, like how does it behave? What does it look like? So there are a few videos that we will look at. And lastly, we'll do backpropagation, or maybe, we'll do backpropagation. So we have quite a few topics to cover today. Okay. So I'll start with regularization. Regularization refers to something quite interesting. See, by the way, I don't know if you are seeing my screen yet. Probably not.
Not yet.
Not yet. Yes. How about now?
Yes, regular.
Nice. So we'll talk about regularization and what it is and how it can help us. See, what happens is, suppose you have 2 data points. I give you something like 2 points. And I ask you to fit some function to it. You could fit all sorts of things to it. You could say, this is one function, this is another function, and this another function that I could put it is. You realize, now between A, B, and C, you would notice that there's a progressive increase of complexity. Now, which of these is the right function? Okay. So it is always a question, which of these should we take? Now, this question is hard to determine when you have just 2 data points. But imagine that you have lots of data points. You have data points like this. Something like this. So now, or maybe I'll decrease the number of points here. Suppose you have data points like this. Right? So you could say that I could fit a line like this. Intuitively, you would like to believe that that is the best line. So why would you say, if you think about it, why would you say this is the best line, best function? And you would say that is superior to, let's say, another function that goes like this. Right, and let me move this white point here, just to illustrate this point. Right? Or illustrate this. Now, you would say that intuitively you feel that the simple blue line is the best. And the reason you think it is the best, or you can check that it is the best, is by a simple measure. You take, this is your training data, but suppose you have test data too. So suppose this is your test data. Let me just mark it with crosses. Some crosses here, some cross here, cross here, cross here. So these crosses are test or validation data. Now, what would happen if you look at the total error, the sum squared error, or average sum squared error, whatever you want to look at, but let's start with sum squared error. You would realize that the blue points has smaller residuals, you know, this, 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 this. Do we see that, guys? That the blue points, I'll just circle the test data so that it's evident to you. The blue points have relatively small residuals. What about the yellow points? Let's look at the yellow points. This yellow is going, let's say, like here. So the yellow residual would be this much, right? The next residual of this would be, do you see how big the residuals are with respect to the test data? This residual would be, well, this hardly looks like a straight line, but imagine it is. And these residuals would be this much, and this point's residual would be, I'm cheating here a little bit, I can't draw the straight lines exactly. But what do you notice? On test data, the residuals of yellow line, yellow curve are cumulatively much bigger in size, right? Isn't it? Much bigger than the blue. So ultimately, you say that that model is best, which makes the least error on test data. So from that perspective, you would say that we should have stuck with the blue line. But that is a little bit counterintuitive, because as far as training data is concerned, and let me mark the training data with a different color so that we make a point quite clearly. This is your, hang on, this is your training data. Where was the training data points? If you look at it, which of these two curves fits the training data better? Let me leave this question here. Which of these two, blue versus yellow, curves fit the training data best? So guys, if you just visually observe which of these is fitting the training data more accurately.
The yellow curve. Yeah.
The yellow one, right? So this is the paradox, yellow. Right? So if you ask from a training data, training loss least for yellow, but test loss, which is what really matters, least for blue, isn't it? So what happened? If you're training and you're not careful, I mean, if you, what you can do accidentally is you can fit a very complicated model and it will go and fit exactly to your data. Are we together? When it fits exactly to your data, it not only has fit to the content, the information content in your data, the generative force behind the data, it has fit to a large extent to the noise in the data. It's very susceptible to noise. So this is called the problem of overfitting, because what you really wanted was the simpler model, the blue model, the blue. You want that curve, and therefore that model which gives you the least error on test data. So this brings us to this a bias variance trade-off that we talked about in a previous class. The bias variance trade-off was that as you dial up the complexity, so for example, if you're talking of polynomial degrees, which makes it intuitive, nomial degrees, how many degrees of polynomial you're taking. So what happens is, as you increase the degree, so increase the complexity of your model, then your loss, if you look at the loss, it's very interesting. The loss for, total loss for training data goes like this. The more complicated your model is, the more it tends towards zero, and it will achieve zero, right? Quite literally achieve zero. On the other hand, if you look at your test loss, and let me use a color, maybe I'll use red for test, right? Test loss, you will observe something very interesting. It tends to go like this. And let me give these names: a test loss, and the green one is, as a recap, this is the training loss. So what it means is that there is an optimal level of complexity at which you should have stopped. This is the place where you should have stopped. And we always search for this point. So how do we find it? It's very difficult, because if you only listen to the training data, then the more complex you make, as you can see the green line, the better your model fits. Your loss function keeps decreasing. So you need some way to tell it that, you know what, you're making models that are unnecessarily complicated. You can get into trouble. Now, in this context, people talk of two kind of forces at work. There are forces that come, errors that happen because of oversimplified models. So let me write those things. A bias errors. This is just a review of what we did, I believe, early on. Bias errors caused by overly simple model compared to the ground truth. Are we together? On the other hand, the variance errors they arise caused by overly complex models. So bias errors are because your model is not flexible enough. Suppose the data is truly like this. Suppose your data is like this, and you build a model which is a straight line. Then the best straight line would be this. If you remember, in data set 2, we did this exercise in ML100. You get a line like this, your best fit line. But this model is underfitting, because it is simpler than the ground truth, right? Simpler than ground truth. So it suffers from bias errors. On the other hand, if you take a model that goes like this, then this model suffers from high, overly complex. It overfits, right? More complex than the ground truth. truth. And so this one suffers from variance errors. Variance errors. So it raises the question that how do we know what is the complexity of the ground truth? How would you know that? And the answer to that obviously is a priori, that is, before doing the experiments, you don't know. Before investigating the data, you don't know. A priori, you can just make some hypothesis about the complexity of the data. So then the question arises, does it mean that I need to keep dialing up the complexity and keep track of the errors? If you look at the test error, do I need to keep building model after model after model and keep looking at the test loss and stop here? Once I notice that the test loss is beginning to climb back up, then I stop right here and say, all right, this is the right complexity of the data. So that is one approach. Right? There is another approach that people use, and that is the approach that is the topic of today. It's interesting, actually. It's almost like having the cake and eating it too. What it says is, suppose we could, and let me take this example and repeat it a little bit below. Hang on, where's my mouse gone? I will reproduce this thing here. Once again, I'll put the data. The data is suppose your data is like this. Right? Now, you know that an underfitting line would be, just to reproduce what we said, underfitting line is this. Well, it's not looking like a straight line. This is your underfit. Maybe I could do better. There is a shape thing somewhere here. Yeah, line. Okay. So your best fit line would be like this. Then your overfit line was, when we talked about overfitting, I said that it was something like this. And this is an, I'm deliberately exaggerating it, but actually this is what, no, maybe I'm not actually. It gets worse than this if you overfit. So this is your overfit line. So you ask yourself, what if we could take a complex model? By the way, you could count, if you're doing polynomials, how many degrees of polynomial it is. How many bends does it have? By the way, why did it become yellow? Eight. Yes. So I'll make it, give me a moment, guys. I will make it blue. So this blue, this line was supposed to be blue. So this is simple. Simple. And this is complex. I'm sorry. This is, let me use the right color for the sake of numbers. Complex. Now, you ask this question that this is 1, 2, 3, 4, 5, 6, 7, 8. So this is a polynomial of degree. Do you remember, guys?
7.
Polynomial of degree.
8 or 9.
Yeah, polynomial of 9, right? It is basically polynomial. At least anything less than that won't do.
Yeah, 8 bends.
Right? 8 bends. So it is a polynomial of degree 9. So the question that you ask is, what if we could have 8 bends, but those bends did not have oscillations? That's the basic question you ask. Can we have, this is too fat. Can we have a model that is, it is all right to have 8 bends, so long as those bends are not harming us. So can we have all those bends, but we dampen the oscillations? This is the question. So suppose I made a model that was like this. Let me build a model, and I'll still give it 8 bends. 1, 2, 3, 4, 5, 6. Oh, no, not this one. Sorry, I take this back. This was a terrible mistake. This is not the line that I want to follow. let me get back. I made a mistake, guys, in my thinking. So let me draw the old model here, and the yellow line, I'll do that. I should be following the data, not this. So suppose you could have 8 band. Suppose your model looked like this. So, what about this? Do you notice that there are quite a few bends in this? Maybe 8 bends. I tried to get it. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, I overdid it by 1. But all right. Suppose you got a model like this. What can you say about it? Do you think that it suffers from high errors, variance errors? That on test data it will do poorly?
Yes.
Why would it do poorly on test data? If you have to compare the blue model, the yellow model, and the pink model, which of these is the best? Which model?
Pink.
Yeah, which model on validation or test will do best? Right? And so somebody said pink. Is there a contrary opinion?
Yes, because it's overfitting, so it shouldn't be the best one.
Yeah, but if you look at that, but it seems to be, let's look at the residual. Remember, the proof of the pudding is in the eating. Think about in your mind, which of these has big residuals and which of them has the smallest residuals?
Yellow has the big residuals.
Yeah, and what about blue? Blue also has big residuals, isn't it? Right. So to illustrate that, if you look at the blue, let's say that this is a test data. So blue has residuals like this. Yellow has residuals like at the same point, yellow has residuals like this. And what about the pink one? The pink one has residuals only like this, tiny residuals, right? Take any other point. Let's take this point here. So here, this point, yellow has residuals like this. Blue seems to have even bigger residuals. And what about pink? A pink line seems to have residuals like this. So in general, which tends to have the smaller residuals? Guys, which of them? Pink. So therefore, you expect that the pink model will perform best. Right? So therefore, so let me write the conclusion down from this. Looking at this picture, diagram, we see that the pink does best. Except that if you look at the pink, it is pretty complex, isn't it? Pink is complex, but we have dampened the oscillations in pink. Right? So we learn a lesson from that. We learn that if somehow we take a complex model, but we can dampen the oscillations, we actually might end up with the best model, isn't it? It doesn't matter. We can start with a complex model, but we just need to dampen the oscillations. So far, so good, guys? That's the lesson to learn. Huh? So maybe I should write the summary here. The lesson is, okay, to start with, a relatively complex model so long as, it's a big lesson actually, so long as we know we can dampen the oscillations. That's the lesson we learn from this particular example. Now, I want you guys to think a little bit and make sure that we got this point. This is an important point, guys. Huh? Any questions before I continue?
Asif, these white dots were training or test?
Oh, just assume that some are training and some are test.
Okay.
Right? So the white dots are the ground truth. So some proportion of them are training data and some are test data.
Okay.
Any confusions, guys? Huh? So this regularization, so this process of dampening the oscillation and not overfitting is called regularization. This dampening of oscillation, this dampening and in the statistical community, they also call a shrinkage. What are we shrinking? The oscillations. We are shrinking the oscillations, isn't it? So that's that. So now how do we do that? So there are quite a few interesting techniques, and in the next hour, we are going to learn about these techniques one by one. But before I do that, let us ask this question. Do we really need it when we deal with deep learning? Are deep learning models complex? Who would like to answer that?
Yes, sir.
It is. They are very complex, isn't it?
Yes.
You have layers. So what do you have in deep neural networks? Suppose you have an input in deep learning. In deep learning, what you have is, how many layers do you want to take? Let's say that you even take 3 layers, right? The example code that I gave you had 3 layers. So suppose you have input x1 and x2 or whatever, and then it goes into the first hidden layer of 128, let us say, and then the second hidden layer of 64, and then the third hidden layer, which is smaller. Let me make this a bit smaller, a little hidden layer. This was the example that we took, and I believe the third hidden layer we took of 16, and then finally, I suppose we are doing some sort of I think I took a single variable. Let's take this, and there was some output, right? So between these, these are dense layers, right? 128 times 64, and then 64 times 16, and then 16 times 1. These are just the number of weights. And then here you start out with 128 weights right here. So you realize that you have hundreds of weights. I think it all adds up to approximately 500, if I remember right, or more than that. Some thousands. So if anybody has your lab notebook open, you can check how many parameters it comes to. Not to mention that each of them have biases, which are also effectively parameters of the model. So what are the parameters of the model of a neural network? Parameters are weights and biases. And so you have a large space of weights and biases. So one thing you can be sure of is that you are looking at a very, very complex model. You definitely run a huge risk of overfitting. Right? See, overfitting, one way of thinking of overfitting is your data has memorized your model has essentially memorized the training data. Right? It has figured out a way to completely fit the training data. So one analogy I can give you is I think this is a little bit off track analogy, but it might work. So when I was in college in the IIT, then I was studying for some subject, right? And I studied the book back and forth and so on and so forth. And then the exam happened at the end of the term. Exam happened, and then I realized that oops, I the guy who got the highest was obviously not me. It was a person who I had never thought really had mastered the subject. So I asked him that how is the world? I saw you having fun the whole time, and how is it that you managed to do so well in this class? And he gave an interesting answer. He says, it's pointless. This professor tends to repeat his questions year over year. And if you know the questions of the last 2, 3 years, if you have the question bank, you can answer it. So he said that in the beginning of this semester, he just got the question bank. Then he went to everybody who he thought was a guru of the topic from the previous batches. He got the perfect answers. Then he wrote it out neatly and memorized it. And sure enough, in the exam, questions came. The questions that came were from that, and he got a perfect score. So let's think a little bit about that. Does he know for each question, did he answer perfectly? If you think about it, yes, he did answer perfectly. Right? It is very much like a model, the yellow model. It goes perfectly through all the training points. All those, if you look at this curve here, the yellow line goes through, the yellow curve goes through all the training points. So you have memorized, it somehow sort of has memorized the data. And so it will always make perfect predictions on the training data. On the other hand, has it learned anything? To learn is the ability to generalize from specifics to other instances. Generalization requires implicitly that you have understood the concepts. What our classmate had not done is actually understood the concept, and he didn't like the topic. I think it was a perfectly legitimate way of getting around and finishing a subject he had absolutely no interest in. But while his method was logical, learning was not his goal. If learning is your goal, then the only way you can test whether somebody has learned or not is to give new data, new questions that have never been given before. Right? And then you would have an entirely different set of results. So in neural networks, you have the same issue because there is so much flexibility. If you give it a finite amount of data, small amount of data, it will just go and completely fit to the data. Huge risk of that. And so it has not generalized. It will make perfect predictions on tests on the training data, and it will make terrible predictions on the test data or validation data.
Asif, I have a question.
Mm-hmm.
So one assumption with regularization is if we start with a relatively complex model, what if we start with a simple model? Do we still need regularization if we don't see overfitting?
No, actually, if you start with an overtly simple model, you are essentially screwed. You can't improve upon that.
But if the simple model is
Underfitted.
accurate enough for the application.
See, if it is a simple, and that is a good question. See, if this line that you see here, the blue line, if it is good enough for your purposes, then you have solved the problem. Remember the old statement, if I may repeat Box's statement, which was, this is an appropriate moment to say that, all models are wrong, but some are useful. Right? Box, the great data scientist, as you would say today, statistician, Box made this famous statement that, see, whatever model you make ultimately is wrong. But if it solves your problem, so for example, in practical real life, if it is useful, the blue model is useful, then who are you to argue with that? Go with it. Are we together?
Yeah.
Asif,
Yeah, I was thinking from a point of view of, especially with deep learning models, as more and more resources are required to run, deeper and deeper neural networks.
Yes.
And if, a relatively simpler neural network can solve the problem with slightly lower accuracy, would we still want to have regularization in that case? I'm guessing as long as, yeah.
Yeah, Nisarg, you have hit an important point actually. So today we live in the world of deep neural networks. One of the things that I always tell people to do is before, suppose it's a classification problem, right? I ask them, did you get a baseline accuracy? Remember, how do we get
Correct.
baseline accuracy? A baseline is just counting the majority class, right? Now you have to look as a lift from that. And I always say that go from simple to complex. Occam's razor principle, the simplest, if the simplest effective answer is the definition of correct. In science, there is no such thing as correct. We do not know whether Einstein's theory of relativity is correct. That question doesn't make sense. In science, we can only falsify or disprove a theory. We can never prove a theory. So what are we doing in science? We are searching for what is the definition of correct. The definition of correct is that which is simple amongst all competing hypotheses, which explains the data. Right? Are we together?
So in the end, I believe the accuracy of the model will still be based on how good is your test accuracy compared to
Absolutely. Yeah. So the test results, the validation results and test results are king. Right? Remember that training is suspect because because overfitting will take place. And with complex models like deep neural network, you will never quite get rid of overfitting unless you bring in vast amounts of data. So this is perhaps a good moment for me to tell you something in practice that happens. See, what happens is because deep neural networks are complex models, if you look at the accuracy, let's look at this, a data set size. Data set size, if you plot it along this axis and you plot some model performance, right? So model performance can be precision, recall, accuracy, some squared error, whatever you measure performance is. So I'll just use the general word, performance of a model of algos, and I'll just use the word algos. What you notice actually is that classical algorithms, the simpler algorithms, they actually achieve a situation like this. They all rise up. Any one algorithm that you take will achieve a situation very similar to this, that they reach a point of saturation. Do you see that this is a saturation point? And beyond this, some point of data set size, D size, at which, beyond which performance of your model does not go up, right? Now, what we observe with deep neural network, and the reason we are so fascinated by it these days, is that deep neural networks go like this. They actually underperform in small data ranges, but at some point, and they keep going like this. Right? So what do you notice? The growth slows down, but it still keeps growing. The performance keeps getting better and better for deep learning models. So if you are blessed with a lot of data, deep learning models tend to outperform other models. Why? Simply because they are tremendously complex, right? There's a lot of parameters, that weights and biases that you can fiddle around with.
In this performance, is it against the testing data or is it training data?
Against the testing data. So let me put all those caveats. What I'm saying is, so we observe a performance of algos against test data. So that is a very good point, Hannah, that you brought up. So we observe in practice that with growing data, deep learning models tends to outperform. outperform other less complex models. This is an observation, but you observe something else. This story doesn't come with its own warnings. What about this region? Let me highlight this region. What about this region? Should you be bringing out your latest and greatest deep learning toys when the data sets are small?
No.
No, you can't blindly assume that deep learning will outperform other models. And you don't know what this cutoff point is. Right? So you should always start with simpler models and gradually dial up. So let me give you a practical thing that I do. Suppose I have a classification problem, and this is something I taught you. What you do is start like this, process. A, the baseline classifier or the 0R classifier, baseline or 0R classifier. What will this do? It will give you a performance that you get even without learning. Data has imbalance. The target class will have imbalance of the classes, right? And one example is, what if you have a test, an algorithm that tells whether somebody does or does not have lung cancer, right? So if you just declare most people to not have lung cancer, you'll be pretty accurate, right? Because most people do not have it. Let's say that the incidence of lung cancer in population is 1 in 10,000. So what does it mean? Your baseline classifier, which doesn't look at the data but declares everybody to be healthy, will still have 99.99% accuracy, isn't it? And it will fail for those cases that really matter. The recall will be terrible as a measure, but it is there. Next, what you do is build a simple model, like the 1R model, 1R model, which means that take only one best predictor and see what happens. And the corollary to this, I often do, let me just call it B prime. I would build a random forest of stumps, depth is equal to 1 trees. So what happens is that you create a random forest in which one particular tree will randomly pick a feature and it will make predictions based on that. So it's a little bit better than 1R because it gives every tree a chance. It's the next level of sophistication. Once I do that, generally I will try out basic algorithms like naive Bayes, or the second step would be, I would try out logistic regression, naive Bayes with Gaussian, of course, naive Bayes, etc. I would try out something simple, right? Logistic, and that subsumes a softmax. I mean, if it is a multi-class, assumes softmax. So you would do that, and you would write down the performance. So performance of A, performance of B, B prime, performance of logistic, right? And now you have a benchmark. Go and do your neural network. And if nothing else, you have a guided path. You know what you're competing against. Are we together? So if your data set is not sufficient, what will happen? If you're in this yellow zone, what do you think will happen? Anyone could guess?
The simpler model will be better.
Yes, what you notice is that the deep learning models are not outperforming the simpler models. So that gives you a hint that maybe this is not the situation for deep learning. We don't have enough data. And so you could try other things, you can keep dialing up. Now would be the time to go to SVM or something like that, right? Or XGBoost. Or boosting. I mean, I use XGBoost in particular, CAD boost. I don't want to go into implementation, but some boosting algorithm boosting, etc. You could try all the things that you learned in ML 100 and 200, and you might have a successful story there, right? Because you're in the yellow zone. And that is something to remember, that even if you regularize and dampen and do things, if the data is a simple parabola, the last thing you want to do is have a deep learning model come out with something like this. Even though it has fit less well than, let's say, simple polynomial regression. Right? That is a lesson to learn. Now, the other thing is, these things don't come without computational cost. Typically, a deep learning model to train takes minutes to hours, to days. A traditional algorithm these days on SVMs can take hours or days, but almost all other things, they converge pretty fast. You can get a baseline understanding by just taking a sample of the data and running with it. Now, there is this other region at the very bottom when the data is really sparse and entirely different set of things shine there. Actually, there's a class of algorithms called the Bayesian methods. Bayesian learning. Bayesian learning is in general a good idea always. In other words, whether you have less data or more data, you should take a Bayesian approach. So it's a topic in its own right, and we won't get into that topic. But one of the things is Bayesian approach certainly works very well when the data set is sparse. The reason for that is Bayesian includes your experience, the domain expert's experience. It is called the prior. You start with an informative prior hypothesis, and then from there you start learning. It is like, let's say that you lost your keys, which seems to happen to me practically every day. So I speak from experience. So not using a Bayesian approach would be to scan the house from one corner to the other, up and down, and look for the keys. A Bayesian approach would be saying, let's take a prior, which says that the keys are probably in my office, for example, where I'm sitting at this moment. Let's start searching from here around this table. Now, common sense would say that's a good approach, isn't it? So that is including a domain expert. Since I'm an expert at losing my keys, you're including my experience into the prior and starting from here.
Do these scale well beyond sparse data?
The Bayesians, they do extreme. Yeah. The only thing with Bayesian is that, see, deep learning is computationally intensive. Bayesian can also be a little more intensive than other models, but Bayesian, see, we live in the world of computational plenty. So to do Markov chain Monte Carlo and the, all of this things that we do, and its variants that we do today is not a big deal. We can easily do it and get away. Right? And if you go and look at the Kaggle, you'll see that there are literally data sets which warn you that they'll be overfitting. And I suppose they're just waiting to see how many people know Bayesians. So maybe it's a hiring strategy. The people who use Bayesians, they will reach out to them and try to hire them or whatever. I don't know. But certainly the winning leaderboard is filled with the Bayesians.
Asif?
Yes.
Can you recommend some algorithms in Bayesian?
Oh, Bayesian. Okay, guys, see, here's the thing. I can. See, the Bayesian is, well, they're all variants of the, you start with MCMC, yeah? Markov chain Monte Carlo, right? And go from there. Let's put it simply like that. And there's a pretty rich literature on that. I offer a course purely on Bayesian. Some of you have been through a few workshops or sessions on Bayesian. Those of you who did engineering math, you remember we did quite a few classes on the Bayesian or sessions on the Bayesian. Anybody here who has taken engineering math and been through the Bayesian stuff?
Yep.
Yeah, I've been through.
Good fun.
It was fun, right? So Bayesian is a different thing. But anyway, this was a big digression from our regularization topic. I
have a question regarding regularization. So you're saying we have to decide on the application of regularization based on the performance metrics, right?
No, 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 Harini, I'm not saying that. I'm saying that if you use a complex method,
Okay.
you must regularize it.
So my question is, how would we know that the model is complex or simple? That is based on the performance metrics, right? How would we know that?
Yes. See, so there is one practical way to know, which is quite simple. See, look at this curve here. Look at this.
Mm-hmm.
When you have a complex model, do you observe that your training data, when you have made a model that is too complex, what do you observe? Your training loss is much smaller than your test loss.
Mm-hmm.
And to build a model and you notice that your training, there is a significant gap between your training loss and your test loss or the test performance. The performance of your training data is very good. The performance on the test data is much less. Then you conclude you are looking at overfitting. You have made a model that's too complex. That is a clear sign. So remember this gap. This gap tells you that you are looking at bigger gaps between test loss, test errors, and training errors is a classic signature that you have overfit.
Okay.
So that's a very practical way of looking at it. Huh? All right, guys. So let me continue for another 10-15 minutes. Let me summarize what we talked. Regularization is asking this question.
Asif, one quick question. So does that mean that, whenever we see there is, we are overfitting. So can we generalize that whenever we are overfitting, we are regularizing the data?
No. Whenever you're overfitting, you have forgotten to regularize, dampen the data. Okay. Regularization is the cure for the disease of overfitting.
Okay, so is regularization, is it part of our implementation? So whether it is simple or a complex, we have to include regularization?
Yes. So it's like you wake up in the morning and you brush your teeth.
Okay.
So a data scientist wakes up in the morning, looks at his model, and if it is not regularized, regularizes it in simple terms.
Okay, so which means that we have to regularize any model we build.
Generally, you should, unless you have a tremendous amount of data and you don't need to regularize.
But how will we know that we don't need to regularize?
Generally, you don't. It's very easy, like I said, right? You look at the error on training, and you look at the error on test, right? So let me give it values, names to that. So suppose the error in test and error in training and test, if E test exceeds by quite a margin the E training, that's how you would know that you really screwed up by not doing regularization. Are we together? This is a clear sign. This is a sign that we have overfitting. Are we together? And let me say that statement that I said a little while ago, that regularization is the cure, is the effort to cure. Well, it's never a perfect cure. Effort to cure the disease of overfitting. Right. So what we are saying is it is okay to take a complex model, but if we can regularize it, if we can remove the dampening in it, then all is well. Because if you can regularize successfully, you actually are doing well. Let's go back to this picture and let us look at this picture here. The blue is underfit. The yellow is overfit. But you agree that pink, which is probably more complex than even the yellow one, is the best fit because we have dampened it down. We have regularized it. Are we getting the ideas across, guys? Anybody who wants to ask any more questions on this?
Asif?
Yes.
So Asif, if the training errors are greater than the test errors, so is that the indication that we need not regularize?
See, when the training errors rarely are in excess of test errors by a wide margin, but if they will be close to each other. Occasionally, you'll see training errors actually are less than test errors. Usually, training errors are more the training errors are more than test errors. When that happens, no, that is usually an anomaly of sampling, data sampling. Your test errors will always exceed, by and large, on average, the training errors. But the question is by how much? If it exceeds by a significant margin, you know that you're overfitting. If it doesn't exceed, if they're more or less the same, or occasionally, you may be having a situation in which you notice that your training and test errors are pretty much matched, then the only thing you can say is that you have not overfit. You might have underfit, but you have not overfit. You might have underfit, or you might have just hit the nail on its head. You might have made just a perfect model.
So in that scenario, we need not regularize, right?
In that scenario, like if you're sure that you don't have underfitting, you're fine. But if it is underfitting, regularization is not going to help underfitting. But the question that you have to ask is, have you missed an opportunity to build a better model? Right? Could you have gotten a more performing model by dialing up the complexity and regularizing it? Right? So in terms of this picture that we have, it would be asking that if I have the simple blue model, there your test error and your training errors would be matched, more or less. But have I missed the opportunity to draw the pink line? That is a question you have to ask. Because the pink curve certainly performs much better. Is a much better model, isn't it? So that question still remains, which is why the preferred approach is to take a reasonably complex model and to regularize it. Okay? Somehow dampen the oscillations in that model.
Asif?
Yes, Dennis?
Isn't a mini-batch gradient descent a way of regularizing?
We'll come to that. Hold on to that thought. I haven't got methods of regulation. We'll come to that one by one, guys. So, guys, is this clear? Yeah, all right, go ahead.
Yes. So, Asif, a little similar to what Dennis is saying. If we implement like early stopping, does regularization influence early stopping also?
Yes. So,
okay.
No, Patrick, you're right. See, early stopping is another regularization technique. It is in the class of regularizers. Now the question is, we will go into the techniques. That's what today is about. In the next 2 hours, we'll do those techniques. But before I do any of the techniques, it is important for us to grasp the concept of regularization. Are we clear, guys? I hope we are. If you have questions, ask me. Otherwise, we'll take a 10-minute break and then come back and do regularization. Techniques, specific techniques.
Asif, then in short, I'm just extending what Sudhir asked you. So that means that like for every model, we have to regularize because we might miss making the model perfect?
Generally, there are ways of looking at it. So, I just alluded to Bayesian learning. One of the beautiful things with Bayesian learning is it auto-regularizes. The regularization term automatically gets baked into the theory. So it comes out. You don't have to do a separate regularization. It is always regularized. There is never a wild oscillations with Bayesian. So that's one positive. But since we are not going to do Bayesian theory here, I'll leave that aside. Generally speaking, there are two choices. you start with very simple models like I do in practical terms, right? What do? I start with very simple models, but I know that with very simple models, it is likely that I have underfit. So I do go through the process of dialing up the complexity. And then at the end of it, when I take complex models, I regularize it. And once I have regularized it, I ask myself this question: did the regularization lead to that pink picture here or not? Right? So in other words, did a complex regularized model give me better answers? Did it become the pink line versus the simple blue line? If it does become the, and you don't know, data is king. Remember, in this, don't forget your no free lunch theorem. Right? You don't know. Ultimately, data will decide which of these approaches will succeed. And that again comes to the thought that in machine learning, you never try one algorithm and say it's good. You try a whole set of algorithms and you of different complexities and see where is it that you're getting your sweet spot. Does that answer your question?
Yeah.
All right, guys. So any other questions before we get into the regularization techniques? If not, let's take it's 8:14. Should we take a 15 minutes dinner break and come back? After dinner, I'd like to have 2 hours straight. So we might extend. Today, we have a lot of theory. If it is okay with you guys, we might extend till 10:30. We need 2 solid hours to cover regularization and to cover backpropagation. All right, guys. So it's 8:15. Let's meet at 8:30. And let's have a quick dinner in 15 minutes. All right, guys. So in the first hour, the summary of what we did is we covered the topic of regularization. We understood its purpose. Roughly, it is to take a more complex model and regularize it, dampen the oscillations, and hopefully get a really good model out of it. When you regularize, you don't quite cure overfitting, but you mitigate it to quite a bit. That's the goal. Right? So now comes the question, what are the techniques to regularize? Now, there are quite a few techniques, and I will give you guys short descriptions of those in the next 1 hour. Now, there's a few, and only those of you who have taken ML 100, 200, you may be, or independently from somewhere, from reading the textbooks and so forth, you must be familiar with L1 and L2 regularization, namely lasso and ridge, and the combination, which is elastic net. I will quickly review that for those people who have not gone through that process, or not become familiar with those regularization techniques, and will introduce regularization techniques that are specific to deep learning. But before I do that, I'll just itemize the things that I will cover. So our topic now is regularization techniques in deep learning. The regularization techniques in this is a big topic. So let me start by itemizing what are the things I'll talk about. One is using L1 terms in the loss function. So what we do is we add some penalty terms regularization or penalty terms in the loss function before we do the gradient descent of it. The second technique that we will use is related, actually. It is something called dropout. Dropout of nodes in a layer. But this is usually referred to, so I'll just highlight the words that people use for these techniques. So when people say L1, L2, they invariably are talking about regularization by adding those terms to the loss function. Likewise, dropout is the dropout is a thing that we will talk about, which is very specific to deep neural networks. The other is early stop. Early stop, and that helps. And then there's more to it, actually. You could do 4. It turns out that something which isn't really meant for that, but does end up having the effect. It is called batch normalization. Now, batch normalization is something very interesting. It was invented in 2015. People started using it. They thought the reason it works, or the problem that it solves, which is something called a covariance shift, mitigates covariance shift. And I'll explain what that means. It was supposed to be doing that. Later on, research found out that it does no such things. So the whole thing has become a little bit murkier. What exactly does it do? But one thing we do know, that batch normalization, it does lead to regularization. It's one of its benefits. And we'll talk about why it regularizes and so on and so forth, and what batch normalization really is. So anyway, if you're reading your books, any of the books, you'll often say that we believe that, I mean, they'll give an example and they'll talk of covariance shift. But just thought I'll put the word out. The evidence is actually not that it does that. It doesn't do that. Now we have a different understanding of the whole thing. Now we had early stop batch normalization. Would somebody like to add something else to this? Anybody has heard another buzzword for
adding noise to the data?
Come again?
Adding noise to the data.
Adding noise is what dropout will do, in effect.
Okay.
But you don't want to deliberately add Gaussian noise to the data. I mean, in a way, you're saying, can we augment the data, perturb the data, and bring? So actually, let me put the other part that is more interesting: data augmentation. Can we use data augmentation to create a regularization? That is a technique. So when we do data augmentation, traditionally we don't do through perturbing the data with noise. I can maybe do a little bit. But what you really do is you look at, for example, images by taking small sections, flipping the image upside down, left or right, lateral flips, or taking sections of the image and working with that, rotating the image and things like that. You do data augmentation. And the last thing that helps is creating an ensemble. Remember, if a random forest is, for example, an ensemble of trees, and because it's an ensemble of trees, it leads to far better regularization, much less overfitting compared to a decision tree. And the same thing applies to neural networks. Whenever you build neural networks, at the end of the day, it often helps to use ensemble techniques. Remember the ensemble techniques of bagging, boosting, and stacking. So I find from experience that using a small ensemble with bagging or taking a few models and then stacking them together invariably leads to better results. You should always do that in the end. Right? Now, always is a rather strong word. It all means, and I must qualify it. See guys, what happens is that when we model, it is for a purpose. There's some business goal, some practical goal. If you are working for weather, if you are working with weather data in a scientific laboratory, your goal is to be able to predict the weather with accuracy that from a business perspective makes sense. So for example, if you can predict the temperature tomorrow at noon within 1 degree, so let's say 70 plus minus 1, that would be considered very good. You don't have to be, you don't have to improve your model so that it predicts down to 70 plus minus 0.0001. Right? That is unnecessary. So one of the questions that always is there is, have you already, like, when do you stop improving? And usually the answer is, if you have infinite time and infinite budget, of course you can go on improving it. It becomes any topic becomes an area of research, and you can keep on improving upon it. But in more practical terms, so long as the goal is satisfied, the prediction goals or modeling goals are satisfied, the performances are within the parameters that you're trying to achieve, you sort of stop there. Right? So for example, if a single neural network is giving you the performance on test data that is within the parameters of what you were hoping for, that was your goal, there may not be any reason to go out all out and build large ensembles and train them, because they take effort, a computational time and effort. So anyway, we'll start with 6, and maybe something else will occur to me. So as you can see, this is a pretty long list of regularization techniques. I will explain what the L1 and L2, I will explain the last, because they have some interesting geometry associated with them. Let me start with the 6th from the bottom up. What happens when you ensemble a lot of them, when you average? To ensemble is to average the results from individual learners. So let's take the example of, this is the wisdom of crowds, isn't it? So you ask people, what is the weight of this object? And people will guess, but if you take the average of it, you will realize that it tends to be a pretty accurate number. Averaging also reduces overfitting, as you can imagine. It reduces oscillations. It smooths things out. Right? For example, if you look at the stock market and you look at moving averages, you notice that they're pretty much smoother than the wild oscillations. So ensembles have that effect. When you take a random forest of lots of trees, decision trees, you tend to get a lot of learners, each tree being a learner, each with a different opinion. But when you average them all out, that's your bagging thing, you take the aggregate value or the majority vote for classification, it tends to do really well. Pretty much similar ideas are applicable to neural networks. Now, one of the fallacies people have is they say, well, isn't a neural network itself an ensemble of nodes? Lots and lots of nodes. So why do we need to create ensemble? The answer to that, of course, is you have different neural architectures that you're putting together. When you put different neural architectures together, or you have trained them with different sets of data, different input features, there is all the more reason to treat each of the neural networks as a weak learner and then to ensemble their results, either bagging it or stacking it and so forth. The stacking is one thing, if you remember in ML200 I mentioned, it is the most overlooked because most textbooks talk of bagging and boosting. They tend to miss out on stacking, though in practical terms, stacking gives you a lot of benefits. So that is ensemble. Ensemble means crowd. It's just a fancy word for a crowd. A crowd of models, right? Crowd of models. So you get the wisdom of the crowds, essentially. And I won't go into it. We covered this a lot about it, that if a model can get its prediction right, let's say binary classification, if it gets its prediction right even just a tiny bit more than half the time, then a crowd of such models are guaranteed to give you much better results. So ensembling. And those results they get better because they also have a averaging or dampening effect on the wild oscillations. That is one. The other way to regularize is just more data. So what do I mean by that? Suppose you have a model. So let's talk about the data augmentation. So there are multiple ways of data augmentation. One is to literally go out in the field and get more data. But if you can't get data, somehow generate more data. Let's say that you have an image. You have an image of a person, let's say this is a person with his hands raised. So what you can do is you can create one more data point by having him this guy stand on his head. Or you could do the data augmentation just by, so this is a rotation, right? You can do various rotations. You can flip left to right, right? So you could do, for example, a right to left, flip, and so on and so forth by various rotations and flips. The thing is, you're training. So suppose this is a cat. You can get a lot more images of cat simply by doing these things. The other thing you could do is you could just look at little patches of the cat. Right? This patch, this region, this region. And so by looking at subregions of an image, you can get more images.